Today we're going to talk about the future of static code analysis and how applying deep learning is going to transform software development. Let me start by stating what we think is the state of software today. I think it's a well-known fact that software has eaten the world, but today the problem is bugs are eating software. And as a consequence of that, software development has become an extremely inefficient process. By inefficiency, I imply the output per dollar per intelligent human capital spent. If we could make this intelligent task more efficient, I think that could transform the way things and products could be built in the future. Why now is the opportunity? And the reason is today we are almost living in the world of collective intelligence in the world of software. Let me explain why and how. There are mega knowledge and data sources that are arising today. Open source software is well known. Then there are social software platforms like GitHub, Stack Overflow, Quora, Google. The infrastructure has completely been commoditized, the AWS, the Azures of the world. IoT is going to increase this data source by leaps and bounds never seen before. And of course, there are tools like Atlassian, Embold, App Dynamics, and these tools are really driving this opportunity of harnessing these massive data sources. And therefore, what I see today is almost we are standing at a cusp of computing history once again. And let me explain what this means. I think when software development really started scaling up, and we go back to 1960, we started building software, and as a consequence, there were lots of added data sources that started getting created. For example, issues, logs, requirements, diagnostic data. From 1960 to 2020, what has happened today is thanks to big data, computing efficiency, a lot of that data has now, we have started making sense and intelligence out of that. Things like correlation engines, prioritization, ranking, deep learning. And I think the next leap and the next change that's going to happen is not going to take us 60 years. It's going to take us probably 10, where we're going to take all this collective intelligence that's being created today and deploy it to actually mass usage. And what we think one industry which is completely underrated today that's going to be impacted positively by this is software development and static analysis specifically. So let me quickly share that why this is happening. It's not science fiction anymore. There are companies like Facebook who have already started using deep learning through their products internally called SapFix, for example, and also the open source community and the Linux Foundation, where they are experimenting with building stable trees using machine learning. So it is slowly getting pervasive in terms of machine learning and software development and code analysis. So let me quickly recap what is conventional code analysis, or what is conventional static analysis, and what it can do. A conventional static analysis is essentially a rules engine that is written for certain behaviors in software that need to be detected, which shouldn't happen. And the way this is done is you have experts / experienced developers who come across a bug or an issue. They write a rule, and the rule goes into the search engine, or the rules goes into the static analysis engine, and you check your code against it. This is the conventional approach, and this is how tools being offered in the market today offer static analysis, which is good, but it has its limitations. A classic limitation is a bug that I'm showing you today. If there was a memory leak that was found during testing and it was fixed, this perhaps would not, if it had escaped the testing process statically, it might have been difficult to find it. And the challenge is the occurrence of these rules happen in different environments. Sometimes you can catch it through static analysis, sometimes you don't. And often if it passes static analysis, you find this bug in testing, in functional testing or manual testing. But then what happens? The knowledge is lost. You cannot be writing rules for every bug you find during testing, which has passed static analysis. So that's the limitation that we see. Taking that forward, if you look at this Venn diagram and we see how does classical testing and static analysis testing differ and what is the overlapping area? Bugs found during classical testing are usually related to business logic or standard conventional bugs related to UI. Static analysis bugs usually detect non-functional bugs that you can find statically. But there is a slight overlap between conventional testing and static analysis testing, which are things like exceptional handling. What I'm trying to say here is there are certain bugs which you can find through static analysis, but which is not often found during the static analysis process and found later in the testing cycle. And the challenge is if you have more and more of these issues which are pushed to being found in testing, which are not found or which cannot be found by the conventional static analysis rule, the process becomes really efficient. And this is where you start looking at very interesting use cases where machine learning and deep learning can be leveraged. Now I'll go back to what I had spoken earlier about these massive data sources, right? Today, a piece of software or a line of code is no longer living in isolation. Today, every piece of software has a certain family of data assets around it. And these data assets could be the requirement for which the software is being written. So that is usually in systems like Jira from Atlassian. And the source code is stored in repositories like Git, Bitbucket, or whatever have you. So there are information sources that are trickling down, which are related to the line of code, which are gone beyond that piece of software. And we have a relationship behind it. So if you look at this diagram that I'm sharing with you, you have a commit of your software. A commit consists of a code change. And I'm taking, and let me just quickly explain what happens in a commit, and I'll generalize it. Every commit that is made in software either is a new feature that has been developed or a bug that has been reported and is being closed or being fixed. These are the two essential commit characteristics you have in software. And I'm now in terms of applying deep learning to static analysis, let's look at those commits which have been used to fix bugs. So essentially what is happening is you have a commit. A commit contains a particular code change which has been made to either fix a bug. So I'm a developer, someone reported a bug against my code, I fix it, or I make a commit and it introduces a bug which is found in testing. But conventional static analysis tools do not have any relationship, or they don't offer a relationship between the code changes and the bugs reported. And that is an interesting use case which can be leveraged by techniques like machine learning to build a knowledge graph, which can then be used to ensure that bugs are not mistaken. Let me take that further. You can now with all these different knowledge banks like Jira, GitHub, Embold, you can now correlate any changes that have been made in your repository and correlate that change to what, and I'm talking about bugs, what kind of bugs did that change report? So did it report a bug related to the design of the code or code quality? And if you can learn from that, you could start building a very interesting knowledge base about changes which can be used. And I'll probably try and simplify that for you. So assuming you made a commit and the commit created an issue, it could be a design issue found by tools like Embold, say assuming it was a God class, and then I fix that. So what you could do is you could use neural networks to learn what changes in code create a certain issue type and what changes in code close the issue type. And that difference can be learned by a learning engine. And that is, I think, the genesis of a very, very powerful application of deep neural networks that will transform the whole learning process in code analysis. I was reading somewhere that 70% of bugs that occur or happen in software in the open source world has happened in the past and someone's fixed it. Usually these bugs are related to synchronization, memory leaks. And if there was a way of learning from the mistakes of these past bugs using machine learning, so for example, what changes in code created these issues, and those changes were fed back to development teams today to ensure the past mistakes are not made, in theory, you could prevent those 70% bugs coming in projects. It's just like I have a team and the team changes hands, new developers come in, and they make the same mistakes again in the code, which often happens. We've heard from large engineering organizations that up to 40% of issues that come up have come in the past and someone's fixed it. So using this simple architecture, if this past mistake learning can be harvested based on this simple diagram and fed back to developers today so that they didn't make the same mistake, you could get massive efficiency. Let me start that with an example. So what you see here is your Git repository. As you can see, these are my commit IDs, these are my commit details, and I was just taking that with an example that we have seen. So assuming a neural network has been trained on a repository, here are my commit IDs. It has also been trained on which commits from your issue system. So this is Kafka, and you can do that. You can just pick up any neural network and you can run this experiment as well. And what I've seen here is, so the model has been created. If you saw my diagram, the model creation has happened. It took me a couple of hours to build the model based on Kafka, GitHub, and Jira. And here, proactively, my model flags this commit, which has, in this there are 12 chain files. It has flagged two potential issues. What this means is, it has found two issues in the code which resembles issues made in the past, and also shows you how it was fixed. So here it says, an other client assigned new task. It says it has found this matching a similar commit that had happened in the past that had created a Jira issue. And for this example, I show you it's created a Jira issue, which is Kafka 6054. I click on it, I go to my Jira. So this is the bug that had happened in the past, which the model finds that I'm trying to create this again. And the model has also learned from Jira that this bug that had come here had created a concurrency and a memory issue. And it says maybe instead of task ID, you should use a new array list, and you could potentially prevent this bug. And this is what I meant. This is Kafka, where in the open source world, people are documenting bugs very well. People are documenting error messages, and you can take all that data and harvest it. And this is what I meant when I said these massive data sources are arising from which you can learn. I mean, you could extend this further and say this issue that it's almost like Minority Report for coding, because it's flagging issues based on past learnings and preventing me from missing it. So it's telling me, Vishal, you're about to create an issue which resembles a past issue, but I could train this model further and could even tell me, by the way, you could talk to Matthias or James Cheng, and they could perhaps guide you or share their experience with you. So at the back, what I think will happen, neural networks will also build this massive knowledge graph, a knowledge network of open source developers, bring them together, and that itself could be so powerful, because today you have no means of using that besides plain natural language text. So maybe there's someone out there who could build a more sophisticated version of Stack Overflow, which is not just a bunch of strings and text, but also has source code, GitHub repositories, intelligence from that, which can be mined and used. So this is an example of how you could use, how neural networks are going to change based on these massive data sources that are being created. Okay, so that was an example that I showed you on Kafka. And what I've done is, it's really fun. You can just build a neural network and train it on open source data sources. So here's another one that we ran it on CloudStack, large data sources, lots of commits, very popular. And this is the development history, as you can see, and it has predicted a bunch of issues. There's one thing I would like to say. If you read some of the papers that is coming out of Facebook research, there will initially be a question on how accurate is the forecast. And I think, as with any neural network based prediction, in the beginning, data shows that it's going to be it's not going to be accurate all the time. So we have to be, neural network based prediction is not 100% in the beginning. It's just like learning. But with powerful feedback mechanisms, with powerful fine tuning, you can start increasing the accuracy, and as with any learning engine. So in large organizations which are experimenting with neural networks and source code prediction, if you can get up to a 50% accuracy in terms of prediction of bugs, and what that means is, if 1 out of 2 recommendations that the neural network based model recommends works, you're doing very well. Because of course, there will be some vague issues which the neural network has learned which may not have relevance. So we assume in the first generation of neural network based recommendation engines in static analysis, you will have lower accuracy. But this is going to get better and better as new algorithms come in, as transfer learning comes in. This will only get better. Looking at this example of CloudStack, let's see. This commit history, it says it sees 10 potential issues. So if you go down to this and see what happens, and it says, okay, this one is it looks similar, but yeah, this is an example of what I say. The recommendation is interesting, but maybe not as exciting. So maybe I'll probably take an example of another one where we see this is more of diagnostics that's coming in from the logs. So it's saying instead of diagnostics, use the other use command in stock.conf, because otherwise you could create an issue. This looks interesting, but this may not necessarily be as exciting as I think. So yeah, this kind of validates what I'm saying. Sometimes the recommendations may not be the most interesting one. Here's another one that I see is formatting the class. It was a mess. See, so the learnings can be funny too, because someone in the issue system actually said this was just get the formatting right, otherwise you'll create an issue. There's another one, and this is interesting. So he's saying if this change that you're writing here could potentially lead to a security issue. And so what is its recommendation is here is, it's in the throw block, but you could just drop the null here, and you could have someone, a malicious user is able to get the size of the cloud by enumerating the ID. So you are actually creating a security issue. And the point to note here is that no rules need to be written anymore. So you're entering the realm of ruleless static analysis engines based on machine learning, and the issues that sometimes these can find are completely catch you off guard. So I think that is one of that's another example that we show where there could be some invalid recommendations, and the model only gets better. So this was just a quick analysis, and this needs fine tuning. But just the example is to show you how neural networks can be used to learn from these massive data sources like GitHub, Jira, Bitbucket, and literally convert all those knowledge banks, all those commit histories, all the issue logs into security analysis tools. So let's look at this diagram. So this diagram explains what I've been trying to show with the previous slide. So you have commits. The commits created an issue which is recorded in Jira. And now you could, then you fix the issue. So something's changed. So this was assuming the buggy piece of code which has been fixed. And then you have fixed this, and then you can see what changes in the code created this fix. And you have the issue description, which is coming from your repository. And then based on that, you can use to train a neural network and predict, and you can almost predict the bugs and the relevant fix to the bugs. So what happens is when you have new code being made, you can do a sequence match of a code pattern that resembles a past bug, and then you flag it as a likely bug, and you also have a recommendation because you've learned how similar bugs have been fixed in the past. So there have been certain experiments that have been done by companies around, and they've found that this technique works really well. And there's very simple testing. You can test it in a very simple manner, the accuracy of your model. What you could do is you could take a code base, say has 100,000 commits. So let's take large code bases like Linux or Chrome or whatever. And you take 80,000 of the past commits to train the model and predict bugs, and then see actual bugs that have occurred in the repository. So it's very easy, right? You take the first, so assuming you take 10 years of data to train the model, you have a project which is 10 years. You take the first 8 years to predict and learn, and you predict bugs which you can correlate to bugs which you actually have in the following 2 years. So take the past data to learn and predict bugs, and use the last 2 years to see if the bugs predicted actually reflect the bug that have been reported, and that's how you can train the model and fine tune it. So it's very easy to apply this. You can do it by yourself. There are all the learning techniques are available, and we think this is a very powerful technique of applying past learnings. Today, you can apply classical deep learning to learn from one repository. However, there are some challenges when you want to train your model on multiple repositories. So there are research happening using techniques like transfer learning. And once that technique of transfer learning is fine-tuned and it works, then in theory, this model that you have can be used to learn from every repository on the planet. So imagine if you could have a model which could learn all the bugs that have ever been made in the open source world, all the different changes in the code which has been able to fix it, and all possible popular programming languages, you could essentially have the most powerful static analysis engine on the planet. So imagine if we could transform the commit history, the issues history of all the repositories available on the planet. And I say the first case is open source. You could literally transform that into static analysis. Why? Because static analysis rules are essentially bugs that you shouldn't have in your code, non-functional bugs. And these bugs are reported through experience. Where does the experience come from? From the open source world. So today it's done manually, it's done by small teams, it's done by people, it's not scalable. But applying this schematic and technique, you could literally train your model on virtually infinite amount of repositories. And I think that is what is the most exciting development you will see in the next 1 or 2 years that's happening. And from our record, there will be solutions like this, or there are solutions like this, or static analysis engines like this in the market. They're probably language specific. However, they are growing, and I think this is going to be one of the most exciting changes in the world of software development that's going to come in the future. And what is going to be the outcome? Because things like missing conditional checks, alternative API recommendations, missing function calls, these are going to be examples of bugs that can be learned based on a repository and fed back, because you technically cannot write a rule for all repository. And there are certain limitations, of course, for any neural network. I think this approach is not going to work if there's not enough data. So if you have repositories with less than 3,000 or 4,000 commits, I think there won't be enough information. But on larger systems like Kafka, Linux, Hadoop, Chrome, Windows, Excel, this is going to be very, very powerful. And I think this change that is coming, will result in an acceleration of software development velocity by orders of magnitude never seen before. So carpe diem and experiment with this, and I'm happy to take questions.